Hello everyone, welcome back to one more video from JEE Advanced 2023. We are taking the question number 5 from paper 1. This question was based on electrochemistry and they had mixed the question from ionic equilibrium where K and alpha they had asked. Apart from that, they had correlated this with the molar conductance lambda with the concentration of the electrolyte, the weak electrolyte what was given. There was some weak acid present. So as usual, we'll be going ahead with the very much detailed discussion. We are having this tagline that most elaborate solutions available online we are having here. So it is going to take time. You need to be patient if you want to learn all those related things which were asked in this question. So this was section 2, which was only one option correct, marking scheme plus 3 minus 1 0. The question was with respect to a curve for 1 by lambda m, which is molar conductance at a given concentration C, was plotted with respect to C, that is concentration in molarity, multiplied by molar conductance lambda m for some aqueous solution of mono basic weak acid HX. For example, we can think of acetic acid was taken, which is giving 1H plus ion, and it is known to us this is giving us a straight line with y-axis intercept is going to be P and slope of this curve is going to be S. We had to find the ratio of P versus S. These are the terms which are explained: lambda m, molar conductance; lambda naught m, limiting molar conductance; C is the molar concentration, that's molarity; and K is the dissociation constant of the weak monobasic acid, which is HX, for example, acetic acid. So what this P by S is going to be, these were the options available. So we'll be starting our discussion from what K is, how it is dependent on concentration, how its alpha looks like. Then we'll go back to the conductance, and then we'll go back to the molar conductance or molar conductivity. And then we'll come back to see how this 1 by lambda m versus constant times lambda m curve, how this would look like. So they have said this is going to be looking like a straight line with y-axis intercept, which is going to have the value P. We'll be realizing that in a moment how that is going to look like. So this Ka, which is dissociation constant, we realize this dissociation constant is going to be defining the equilibrium concentration for the dissociation of that acid, which means if you are having the acid which is giving H plus ions in reaction medium, it will be forming hydronium ion in the solution, and there will be some conjugate base. If it was acetic acid, we'll be getting here acetate ion, for example. Here we can be getting whatever that ion. If the acid was supposed to be acetic acid, then this conjugate would have been CH3COO minus. So the dissociation equilibrium what we are having, HX plus H2O giving us 3 plus X minus ion. This dissociation equilibrium, how far this goes into the forward direction, is defined by this Ka. So we have written this is concentration of hydronium ion into concentration of X minus N divided by HX. This tells us the quantity. This is the basically quantification of the extent of ionization of the weak acid, whatever was present in the given solution. And as we say, it is quantity. If you have larger value of Ka, that means stronger the acid is, which means there is a greater tendency to ionize, which is going to produce greater concentration of hydronium ions in the solution. That is how Ka should be read. Ka is related. We all JEE Advanced students are very well aware of that, what Ka is, how does it compare with the hydronium ion concentration or with the alpha. Coming to alpha, we say this is the extent to which a compound dissociates into its ions. So that HX what we have taken if you start with the 1 mole of HX, then how many moles of hydronium ions you are getting? That is the extent of dissociation or degree of dissociation, which we are calling as alpha. So this is basically the, again, measurement of how much percentage or fraction. If you are writing this with 1 mole of the compound, this is going to be fraction. If you start with 100 molecules of the compound or 100 moles of the compound, this will be representing as percentage. So how much percentage it is going to be, and maximum percentage for weak electrolyte, it can be 1. A maximum fraction, that's 1. That's complete dissociation, which translates to 100% dissociation. So if you have got AB, some general expression for any given electrolyte, this is going to dissociate into A plus and B minus. Degree of dissociation as defined alpha, we are writing here. Sometimes it looks like A. So degree of dissociation alpha is defined as the number of moles of the compound dissociated divided by number of moles of the compound initially taken. So out of 10 moles of AB, let us say if 5 moles are dissociating, it is going to be 5 by 10 is the degree of dissociation, which translates to 1 by 2, or it can be written as 50%. So this is what we are writing as alpha is A plus or B minus if it is AB type of the electrolyte. If it is something different, we have to write it accordingly. So either A plus ion concentration or B minus ion concentration divided by total AB ion concentration taken in the beginning. That is what we are calling as the degree of dissociation. And this degree of dissociation can be ranging from 0 to 1, where writing there's a fraction. In percentage, it can be going from 0 to 100. So if it is 0, it implies this is no dissociation. That compound is basically not behaving as an electrolyte. For example, if you are putting, say, some benzene in water, or something which, let us say, dissolves, say we are putting glucose in water. So then this is zero dissociation happening. And if you put something which is very highly soluble, which get converted into ions very easily, say cesium fluoride, that's going to have the degree of dissociation as 100% or 1 in terms of fraction. That is how alpha compares with the Ka. Now we will be having a brief discussion about what factors are there which are affecting the alpha degree of dissociation. The very first factor is the nature of compound. So when we are having stronger compounds, for example NaCl, they will be having greater dissociation in comparison to weaker electrolyte, say for example acetic acid or ammonium hydroxide. So if stronger is the compound, it is going to give you more dissociation. That's actually the reason why we are calling them stronger, which means they are going to be almost completely dissociated. This is going to give us almost 100% dissociation. Alpha is going to be nearly 1. And the second factor is the concentration. So when we are having higher concentration, then less number of ions are being produced. If you are having more dilution, which is lower concentration, we will be having more dissociation. And we had something we called about that is called something, this rule called Ostwald dilution law, which tells for the weak electrolytes, the alpha is actually equal to K times square root of C, which we sometimes are writing as alpha is equal to K times square root of V. So V stands for dilution, C stands for concentration. Alpha is inversely proportional to concentration or directly proportional to dilution. More the dilute solution we are having, more will be the value of alpha for the given case. Next factor is temperature. We know when temperature is kept higher, molecules may be having higher kinetic energy, and with the higher kinetic energy, there may be greater and greater dissociation for any given electrolyte. So temperature will be having increasing effect on the degree of dissociation alpha. Also, there is an important point, which is pressure of the other species which can be present in the solution. So if you are having the other substance like which can be exerting common ion effect or reactive ion pair effect. These two things are which will be very much affecting the degree of dissociation for the weak electrolytes in particular. So when we are having any common ion present from some strong electrolyte, this will be suppressing the dissociation of weaker electrolyte in particular. This effect would be there in the strong electrolytes as well, but this is much more pronounced for the weaker electrolytes. And then we have the opposite effect we call reactive ion pair effect, which is when one ion from the weak electrolyte is combining with the another ion from the strong or weak electrolyte. This time the other electrolyte can be weak or strong, doesn't matter. If it is reacting, so suppose this is A, B kind of electrolyte, and this is producing some A plus ion and B minus ion. Assuming that this B minus ion is combining with something else, let us say there was something XY, which dissociated to produce X plus and Y minus. If B and X are combining to form XB continuously, this equilibrium, which was earlier not very much in the forward direction, let us say earlier this was having degree of dissociation as 1. Sorry, earlier it was having say degree of dissociation as 0.1, 10% only it was dissociating. So in presence of XY, doesn't matter this XY was weak or strong, as it is generating some X plus ions. X plus ions are combining with the Y minus ion, and these are being depleted all the time. So if these are being depleted, this equilibrium will be tending towards in the forward direction, which implies more of the AB will be dissociated. That is what we are saying, the degree of dissociation is going to increase, and these effects are very, very pronounced for the weak electrolytes. Their situations can be reversed. They can be very strong effect on the degree of dissociation when the common and or reactive ion pair effects are present. We are using these effects actually very much in the qualitative inorganic analysis and elsewhere in the different cases of the this ionic equilibrium, and very much in the organic reactions as well, where we are driving the equilibrium by the presence or the absence of species in our given solution. Okay, going forward, we'll be now writing the mathematical expressions. So suppose we are having some HA kind of weak acid. This is being dissociated into H plus ions and A minus ions. Earlier, although we had written HA combining with water, if this was an acid, this is supposed to be converting into H3O plus and A minus. Many times we are writing H plus ion and hydronium ions synonymously. We have written here just like HA is giving you H plus ions and A minus ions. Now in the beginning, when there was no dissociation starting, concentration of HA we have taken as C, and the concentration of H plus ions and A minus was 0 each. When this equilibrium has been established, when equilibrium is there, that's C equal to equilibrium. So if some C times alpha amount of HA is being dissociated, initially it was C. Let us say 1 mole of the HA was taken, and out of this 0.1 mole of HA is being dissociated. So 1 times 0.1, that is 0.1 mole, 1 by 10 moles of HA is being dissociated. So as many moles are dissociated over here, those many moles of H plus ions and A minus ions will be produced. So C alpha is becoming the concentration of H plus and A minus ion. Now we can be writing this expression. Ka is going to be concentration of H plus ions. This is the concentration of A minus ions, and this is going to be the concentration of HA at the equilibrium. This is the Ka. Here we are writing these concentrations at equilibrium. These concentration at equilibrium, these concentrations at equilibrium. And the concentration at equilibrium we have defined here, K is equal to C alpha square. One C term we can cancel out from here. So this is going to be C alpha square divided by 1 minus alpha. That was all about the Ka and alpha. Now talking about the molar conductance. What molar conductance is, this is the, we defined the way, this is specific conductance of a solution. If you keep 1 mole solute, which is dissolved in a solution with electrodes kept at a unit distance. Usually when we are doing experiments in lab, we keep this units as CGS units. The reason is we cannot afford having 1 meter cube of a solution for an electrode. That will be a huge wastage of chemicals. There will be a very much problem in passing current and doing all the calculations which may be involved. So 1 centimeter cube will be very much practical thing, and no wonder whenever we are doing questions, when we are solving, when we are seeing problems, we are using the units mostly as in CGS unit, as long as the conductance things are correlated. Like we will be writing the units in, say, centimeter Siemens per centimeter per mole, whatever. Those kind of units we are writing whenever we are writing the molar conductances. We are rarely writing these in the terms of meter square or meter cube, something like. So specific specific conductance of a solution when we have taken 1 mole solute, we are calling as molar conductance. Similar term is we call equivalent conductance, and that is when you have got 1 gram equivalent solute put into between the electrolytes which are having unit area of cross section and which are separated at the unit distance. Talking about specific conductance or conductivity, this is defined as the conductance of a solution which is having unit area of cross section and which are separated by unit distance. We will be coming back to the specific conductance in a moment. First, we need to go back to even more basics of this electrochemistry. So we have got coming from the Ohm's law that this resistance is equal to resistivity rho into L by A, where L is the length of the conducting wire or any solution, and A is the area of the cross section of the wire or any conducting solution. R we have been calling as resistance, and rho we have been calling as resistivity. L by A have usual terms. L is the length, A is the area of cross section. Now, in conductance, we are defining this as the opposite of resistance. So what we have been calling in physics as resistance in the case of conducting wires, in case of conducting solutions, now the reverse of resistance we are calling as C, which is conductance. And as this was a rho resistivity, which was sometimes called as specific resistance, resistivity, the reverse of that we'll be calling as conductivity. Rho was resistance, so C we are calling as conductance, and as rho was resistivity, the opposite or the reverse of rho is kappa, it looks like K, we are calling this as conductivity. Also, this conductivity we are saying as sometimes specific conductance. Just like resistivity is specific resistance, conductivity is specific conductance. Now, if you put both these values, C and kappa, this becomes R becomes 1 by C, rho becomes 1 by kappa, and that is L by A. Rearranging this expression gives us this thing. We are writing this as kappa, that is specific conductance, is equal to C, that is conductance, into L by A. And this L by A, when we are talking about the solutions, we are using some conductivity cell. This conductivity cell looks like some round bottom flask, very small flask, where 2 platinum wires are fused, and they are approximately 1 centimeter square, and this is their wires are coming out and they are fixed from here. We have here some inlet for putting some electrolyte inside. So let us say this is some solution which we are trying to measure the conductivity of. We are putting the solution from here, and these are the conducting wires which we can connect to the external circuit, and we can measure the resistance. So for this conductivity cell, what we have written, the area of cross section of these platinum electrodes, that does not change. That is your A, that remains constant. Also, the distances between these 2 electrodes, that is considered as L, that also for this given conductivity cell does not change. So this L by A we are calling as cell constant. The cell constant should be considered as conductivity cell constant and not that galvanic cell or electrochemical cell constant. So that cell constant for a given problem, whenever we are given, we will be keeping this as a constant. If in the first section they have given some data, that can be giving us the value of L by A. And if the same conductivity cell is used somewhere later in this problem, if they are not specifying anything else, we will assume the same conductivity cell has been used. So in the later part of the questions, the same value of L by A has to be used, and that is why we have used this term cell constant, that is remaining constant for the given problem. It is very much clear that if we are doing some experiment, we will not be using different kind of conductivity cells. We'll be using just one fixed conductivity cell. There only we'll be removing the liquid. I'll say earlier you are having KCl over here, you'll be conducting, doing measurement, then you'll rinse it out, and then you can be putting another solution. Say you are doing acetic acid, so you'll be putting acetic acid here, and you'll be doing another measurement for the value of the conductance or resistance. And resistance actually we measure over here using Wheatstone bridge, which we have seen in physics. So the side of the one side of the arm, let us say P by Q, is going to become R by S when the bridge has no deflection or bridge is having no current flowing into it. That was the thing we have seen in the Wheatstone bridge in physics. Okay, moving on, we have here something which we have defined as specific conductance. So as per Ohm's law, we know that V is equal to IR, where I was the current, we were using units of ampere, V was the voltage, units we are using as volt, and R is the resistance, we are using the units as ohm. Now we understand that this expression what we had written, the resistance depends on the volume between two metal plates. So when we are keeping the values of L by A as a constant, and then resistivity is becoming here same as R, and the L by A we are calling as that cell constant. The units of this is going to be usually centimeter, and resistivity is going to be in the unit of ohm meter. Mostly it is going to be ohm centimeter, at least in the electrolytic situations. So because we are relying on this kind of construction of the diagram, this is going to be inside our conductivity cell. This part, this is going to be one platinum electrode, this is going to be another platinum electrode, and they are supposed to be separated by 1 centimeter. The surface area of this platinum electrode is supposed to be 1 by 1, that is 1 centimeter square. So when we are keeping something inside this, you have taken any solution, you keep that solution in this area, in this volume we should say, when we are keeping any solution in this volume, and then we are going to measure the resistance, we'll be doing 1 by R, that is going to be the value of the conductance of this particular solution. And if we have the value of L by A, in this case L by A is going to be 1, so when L by A is going to be 1, the kappa is going to be same as C. That is how we'll be defining the conductance, which is 1 by R. So conductivity is going to be a reverse of that. That's how we can be comparing these two values, and we can be figuring out what is going to be the conductance or specific conductance. Here we have got, once again, we are trying to keep the solution inside this 1 by 1 centimeter, that is 1 centimeter square. Keeping your solution over here can be giving us, as you allow the current to pass through it, you will be having some resistance experienced by the charge carriers, whether this is a positively charged ions or negatively charged ions. They'll be feeling some resistance, they will not be freely moving. So that whatever resistance they are feeling, we can translate that into the conductance. Coming back to the definition once again, conductance of a solution where the electrodes have got the unit surface area and they are separated by unit length. This is called as specific conductance or conductivity. Going further to the molar conductance, which we wanted to go in detail, this we'll be going in even greater details. We understand that the conductive solution, which is going to be divided by the molar concentration of the electrolyte, we are calling as the molar conductance. So basically you have got 1 molar solution, then whatever conductivity of the solution is going to be, that we can be calling as molar conductance. If this is any other value of the conductance, we have to make the suitable adjustment accordingly. And this is going to basically tell us about the ability, how easily our solution is going to carry the electric current in the solution. How easily current can be passing through a solution is the measurement of the molar conductance. So the solutions, or rather the electrolytes, which are having more number of charge carriers possibly present in solution, they can be giving us relatively better conductivity. Or if there are two different electrolytes and they are going to produce the same number of charge carriers in the solution, the number of other factors can be responsible. Those factors we are going to talk about one by one. So our basic idea would be in which case our charge carriers can be moving easily, because if they are moving easily, they are having less resistance. Less resistance implies more conductance. More conductivity will be translated into more conductance for the same given case, that in every case we have taken 1 mole of the solute in the given solution present. Talking about what are the factors affecting the molar conductance, the first factor is ionic size, or the size of the ions. We understand when the size of ions are going to be relatively bigger, we will be saying they are going to have much lesser conductivity, because the very bigger sized ions will be having much greater resistance felt, because lot more number of solvent molecules, they need to move from their path when they are moving. And it is important to note that this ionic size should be compared with the size of the hydrated ions. We have seen this in some of the earlier discussions, that size of hydrated ions should be compared. For example, if you talk about lithium ion, which is aqueous, this is way bigger in comparison to number of other ions like sodium ion aqueous, which is bigger than potassium ions aqueous, etc. On the contrary, if it was the gaseous ions or isolated ions, then lithium would have been the smallest and potassium would have been largest of the three. Going further, rubidium cesium would be even larger. Second point on the factor affecting, so the idea over here was lithium ion is very big in size, so lithium ion will not be finding to move easily. We sometimes say the hydrated radii, because we are in the case of the aqueous solution, it is not lithium which is going to be lithium gaseous or lithium isolated, this is going to be lithium aqueous. So hydrated lithium ion will be having way bigger radii. Hydrated lithium has biggest radii for the alkali metals. So this is not going to move easily. This is going to have the this is the size of the hydrated ions. So their conductances are going to follow the reverse order. So the conductance of these ions is going to be, we'll be seeing in a moment this data coming from different experiments. So the conductance of lithium ion is going to be now smallest, followed by sodium, which is going to be having better conductance, followed by potassium, which is going to have even better, and other ions could have got even better. So rubidium and cesium will be even better in the conductance in comparison to lithium ion. Charge density is again going to be inversely proportional, because greater the charge is being accumulated onto our ions, they will be attracting the solvent molecules much more strongly. Say you have got lithium ions and you have got beryllium ions. Lithium and beryllium ions are kind of almost similar in size. Beryllium is very little smaller in size, although, because of greater charge density, because of greater Z factor, we should say. Now there's another problem. Lithium and beryllium. Lithium has got 1 unit positive charge. Beryllium has got 2 unit positive charge. With almost similar sizes of lithium and beryllium, beryllium has double the positive charge. Very high charge density on beryllium will not allow it to move very easily in the aqueous medium or any other solvent. So this is going to have very high resistance. And very high resistance translates into very poor conductivity. That conductivity will be translated into the molar conductance as well. The next point is the solvent viscosity, and this is very much intuitive that if your solvent is having very high viscosity, it will not allow its layers to be moving very easily, or anything else which is coming between its layer. Those things will not be moving very easily because those solvent molecules are going to be attracting each other. Something disrupting these forces and moving along the liquid will be not supported very easily unless and until some electrical field gradient and the attractive forces on the charge carriers is actually able to disrupt these. More the viscosity, less likely that any ion can be moving across it. Temperature is going to be directly proportional to the conductance because temperature has twofold effects. Number one, it decreases the viscosity of our solvents, and it also increases the kinetic energy of our cations. And if you are having weak electrolytes, it can be threefold effect where it can be increasing the degree of dissociation as well. So temperature is going to be increasing our molar conductances in all the cases. We have got concentration, very, very important, and this is the thing on which our question is based upon. So concentration is going to be inversely proportional. If you are having very high concentration, then the oppositely charged ion, say you have taken sodium chloride. So if cation and anion are not very much separated from each other, there can be very little solvent molecules present here. If that's the case, cations and anion can still be feeling attracted towards each other. Moving these ions in presence of electrical field may not be very much favorable. If you want that to happen, you may need to apply even higher potential. So for a given fixed value of potential, when you are comparing with something when the solution was relatively diluted, these cations and anions may be relatively farther apart. So let us say we are diluting this thing. Upon dilution, what is going to happen? These cations and anions are going to move farther because now there are so many solvent molecules coming in between. Now each of the cation and anion can be moving very, very easily, whether this was the case of strong electrolyte like NaCl, or it can be weak electrolyte like C3COOH. For weak electrolyte, there is one extra effect that this can be having its degree of dissociation increase. We talked about earlier in the factors affecting alpha. So that can be having much more effect on the molar conductance when we are doing dilution of the solution in comparison to the strong electrolytes, which were already very much dissociated, or we can say almost 100% dissociated. The only difference is that solute interactions can be minimized in cases of dilute solutions up to much greater extent, even for the strong electrolytes. So dilution will be playing its role for the strong electrolyte like NaCl, as well as for weak electrolyte, say for example acetic acid. And this effect of change in dilution will be much greater for the weaker because there is degree of dissociation also changing. In strong electrolytes, this is only solute interactions, or cation anion interactions are only going to be minimized. There, apart from the cation anion interaction being minimized, there is increase in the number of charge carriers as well. More number of ions being produced, that will be increasing the molar conductance or conductance even further. Then we have got presence of other species as well. So when we have got other species present, there can be two kind of effects. Number one, if there is more molecules are joining together, that can be happening in the cases of complexation, dimerization, or precipitation. If that is happening, then there will be less number of charge carriers present. That will be decreasing the conductance and henceforth molar conductance of the solution. If you are, on the other hand, talking about interactions like ionization or dissociation, then there will be increase in the number of charge carriers, and then that is going to increase the conductance, and that increased conductance is going to give us the increased molar conductance as well. So these are all the factors which are affecting the molar conductance. Sometimes these factors can be interacting with each other, and overall molar conductance can be influenced by their combined effects as well. Now we'll be taking some of the effects even further, and we'll be going deeper into all these effects one by one. We are taking for the first the factors affecting ionic size and the charge density. We know that ionic size is going to be inversely proportional, and charge density is also going to be inversely proportional for the conductivity of these different ions. This is data taken from the book by Robinson and Stokes, the book called Electrolytic Solutions. We have two things to note here. First of all, we are talking about when we are going from lithium to sodium to potassium to rubidium. As we talked about earlier about their sizes, you can see going from lithium to sodium, conductance is increasing. Going from sodium to potassium, it's increasing again, and this is increasing again. So for the same group, when we are having same size of the ions, as the overall size, the hydrated ions size is going to increase, we are going to see that there's going to be decrease in conductivity. So lithium, biggest in size, least conductivity. If we compare here the lithium and beryllium, the conductivity is changing from 38 to 90. This is going to be more than double. What happened to the factor we are talking about, charge density, should be inversely proportional. That is true, but while doing this comparison, we should be talking about the same charges of the ions associated in our discussion as well. The reason being, in the same electrical field, when these ions are moving for the same potential difference applied, the way lithium ion can be moving and the way beryllium ion can be moving, there will be huge difference in the attractive forces being applied. So we cannot be comparing lithium and beryllium directly because their attractive forces are going to be completely different. Although the charge density will be affecting their overall values, like for example, if you want to compare copper and zinc, their sizes are almost comparable, and the hydration of these two can also be quite comparable. Both of these are having 4 coordination numbers, so 4 water molecules can be joined together. And from the discussion of the D block elements, we remember that from copper to zinc, size was increasing only a little bit. So that small difference in the size can be seen, like in comparison to copper, zinc is very little bigger in size. So as it is very little bigger in size, that small difference is going to change its conductance by smaller magnitude, in the sense that zinc ion, which was a little bit bigger, can be having a little bit more resistance, and because of little bit more resistance, its conductance can be marginally smaller in comparison to that of copper ion. And coming back to the discussion of these 2 points, what we have taken, one is about hydrogen ion and one is about OH minus ion. We can see H plus ion's conductance is far greater in comparison to rest of the cations whatever we are having here, and the very same way the conductance of hydroxide ion is far greater in comparison to rest of the other ions given in the table. Explanation of this thing, why H plus ions and OH minus are behaving this way, why they are exceptionally higher, why they are having their values unusually high. We have got there has to be some explanation. We'll be discussing about that. There is some different mechanism actually for that in comparison to rest of the ions we are seeing here, either in the cations list over here or in the anions list over there. Here we go. We call this different mechanism basically. The first case, when rest of the normal ions are moving, we are calling it as they are basically getting transported from one place to another. That we call as vehicle mechanism. And for the case of H plus ions and OH minus ions, this is not vehicle mechanism, like they are not actually getting transported from one place to another. This is called Groth's mechanism, where something different is happening. We'll be seeing that what was the case. So conductance of ions is following two different kind of mechanisms. The first one, which is vehicle mechanism, is followed by all the cations and anions other than H plus ions and other than OH minus ions. Only cations and anions which follow Groth's mechanism are H plus and OH minus ions, and that too in presence of any of the protic solvents. Protic solvent has to be present, then only this kind of mechanism, Groth's mechanism, is going to be possible. That spelling should have been Groththus. Okay, this one is the correct spelling. So what we are saying, the net result is H plus ions and OH minus ions appear at the new places by this Groth's mechanism, in which your hydrogen might have been present in the beginning over here, and soon after this is going to appear over there. And actually this H is not being transported from here to there. What is happening? This whole hydronium ion which was present is losing one of this H plus to another water molecule which may have been present over here. If that happens, this molecule converts into hydronium ion. I'll highlight using this. So earlier this was one H plus and this was one water molecule. This H plus combines over here, we are getting hydronium ion. Now this is another water molecule. This is taking one H plus ion from here. This is converting back into the water molecule. This H plus ion is getting transferred from this water molecule over here, and this continues further. So this H plus ion from here appearing here, appearing here, appearing here, and then appears there. So H plus ion disappears from here and appears over here. This is something unusual in comparison to rest of the ions. This is what we are calling as Groth's mechanism. This way H plus ions can be having its conductance way ahead in comparison to rest of the ions what we are comparing, and same thing happens for the OH minus ions as well. So H plus and OH minus ion will be appearing at the new place without actually being transported physically from one place to another, as happens in the cases of vehicles. We move them from one place to another. That is how we are comparing vehicle mechanism versus Groth's mechanism. Once again, what happens in this Groth's mechanism is we will see with the help of one animation. So this is how water molecules are going to change their H plus ion. So this was water molecule, it is transferring one H plus ion, and this is continuously moving further and further. So you can be having the movement of H plus ions going from this side, and they'll be appearing over here onto the another side. This is the meaning of the Groth's mechanism. Sometimes we call this thing as the proton hopping in comparison to the vehicle mechanism for the other ions. So a similar kind of thing is supposed to be happening to the OH minus ions if the protic solvent was present. It can happen in the case of water, it can happen in the case of ethyl alcohol or methyl alcohol, but aprotic solvents, this kind of thing cannot happen. So this was the comparison in vehicle mechanism. Something need to be transported. So this person is going to transport this ion. This is going further. So this person is going right. This person is going right. This person is going right. This is how things are being transported. Then there are other person which are coming back to collect some new of these pieces of these ions. They'll be getting and collecting things. This is a kind of vehicle mechanism. But in proton hopping, something different is happening. This person is taking that object and passing on to this person, that is passing on here, and there is no physical moving of the people over here. They are standing in their own places. They are just passing that object, that ball or anything like proton in this particular case, we can say. That was Groth's mechanism. So aprotic solvent, this thing is not happening. This is happening only and only in the case of the protic solvents. Here we have one proof. We have taken some different solvents. In this left image, the diagram number A, we have taken water as the solvent, shown with square over here. Then we'll be taking methanol, shown with the circle over here. Then we are using ethanol, shown with the triangle over here. These were all protic solvents, and in spite of being a protic solvent, their ability to transport H plus will be changing depending upon their dielectric constant, we can say, or their ability to accommodate H plus, we'll say. On to the right, in diagram number B, we are having some aprotic solvents. We are having dimethyl sulfoxide, shown with this delta sign over here. We have acetonitrile over here, shown with the square in this curve, and also we have nitrobenzene, shown with the circle over here. So if you see, we have here taken some different cation source, that is HMIM, which represents for imidazolonium formate, that ion is here. So H is there is protonated imidazolonium ion. Imidazole is basically getting one H plus ion. We are calling that as imidazolonium, and there can be one alkyl group present as well. This is the meaning when we are keeping in this imidazole ring, we are keeping one methyl group onto the nitrogen group, and then another hydrogen is being protonated. This is we are abbreviating as HMIM. And it's because it is a counter, it is some positive charge, its counter ion has to be present. We have used counter ion as formate. The theta is belonging to that particular compound. And this is the structure of, we are saying, imidazolonium based carboxylate, RTAIL. RTAIL stands for room temperature acidic ionic liquids. I'm very much sure you might not have seen ionic compounds which behave as liquid at normal temperature. Most of the compounds which we have seen which are ionic are supposed to be solid at room temperature in general. These are few of the compounds. This imidazolonium ion is one of the ions which has most of the whatever anion we are keeping, formate, acetate or propionate, they are liquid at room temperature. So we are using this term RTAIL, which is room temperature acidic because this is having that acidic hydrogen present as well. Room temperature acidic ionic liquids. This is the imidazolonium formate. This data is about that. Coming back to our main point, you see, when we are having water present, the conductivity of this H plus ion which can be coming is ranging from 108, and this is the concentration thing. As we are changing the concentration, this is very low concentration, this is very high concentration. There's a range, and this range is about 108 to say somewhere about 98 or 90, something like that. That's range. As we are changing our water as a solvent to methanol or ethanol, this conductivity value you can see is decreasing from this particular range. This is going to here, this in the case of methanol. And ethanol, because that ethyl group is going to not allow the protonation happen or deprotonation from imidazolonium to happen very easily, this is going to have the value of the conductivity even less than that. That was happening in the cases of all these solvents which were still having Groeth's mechanism possible, and that mechanism of ion transport can be still going that particular way, although it is decreasing as you are replacing your water molecule where both of the hydrogens were easily replaceable in ethyl and methyl alcohol, that is just restricted to one. A huge difference in the conductivity has been seen, molar conductance. Over here, when we have taken apolar solvents, non-polar solvents, about the similar range of the conductivity even we are having here, similar ranges of conductivity we are having here. Now if you see, this scale was about 10 over here for ethanol. Now this scale is starting from about 5 and this is going down to about 1. All these solvents which are aprotic solvents, now Groeth's mechanism is not possible, so their conductance across all these variations of the concentrations is going to be way smaller. And of course there is quite differences in the conductance as you are changing the concentrations. DMSO and acetonitrile can be having differences in the conductance because they can be having different kind of ion dipole interactions associated in comparison to nitropentene, which can be having a relatively smaller of these kind of interactions. So that was the conclusion about how the Griffiths mechanism is helping these things move, H plus ions and OH minus ions move much faster in comparison to rest of the cations and anions. That was the plot of lambda versus concentration for imidazolonium formate at 298 Kelvin. Going further, we have got the variations of viscosity, how viscosity was affecting. And we talked about all this already, that viscosity is inversely proportional to the molar conductance. This is basically after Paul Walden, who basically had seen this variation about different solvents, and he used some compound tetramethylammonium iodide, which is ionic compound. And he saw that the correlation was this lambda is the molar conductance and eta is the viscosity. Their product is going to be constant. So this Walden's rule is a very clear indication that the viscosity and the molar conductance are going to be inversely proportional of each other. And this is suggested by Keith J. Laidler, one of the renowned people in the name of the molar conductance and even in chemical kinetics for physical chemistry as such. Next factor we are going to see is the temperature. This is again the data taken from the same source. Okay, that's from the Handbook of Chemistry. This is changing when you are having, this is the temperature 288 Kelvin, and you are changing from 288 to 313. You can see whatever cation or anion you take, irrespective of the nature of cation, every time you are going from left to right, the conductance is going to increase. And we have taken here basically the rate of the limiting ionic conductance, which is the conductance when the concentration was approaching 0. So when basically no ion interactions are present, our ions are free to move. In those cases, increasing temperature is going to increase the molar conductance very easily. And why we are not doing so at very high concentrations? Because at very high concentrations, the ions can be having a situation kind of what we see happening in the cases of conductivity of metals, where too much of the vibrations of one particle can be hampering, like too much of the kinetic energy of one particle can be hampering the movement of the other ion, which can be moving in the opposite direction. So limiting molar conductance is giving us much better idea how these conductances are going to change. Okay, now coming to the last point, that was concentration, and we have seen this concentrations variation in the alpha degree of dissociation. That is being translated here as well. So what we are seeing here, when we are having very strong electrolyte, their conductances values for any given concentration 0.1, 0.2, 0.3 are going to be way higher in comparison to weaker electrolytes, which are going to have their value very small. Intermediate electrolyte, which can be having say 50% dissociation or 40-60% dissociation, they'll be having their values in between. There will be sort of intermediate electrolyte like that. So as we are going to change the value of the concentration, and basically this is square root of C. So when we are going to change the value of the concentration, then there will be change in molar concentration, molar conductance as well. Now this change, what we are talking about, the delta lambda, this one, for a same change in delta C. Let us say we are changing the concentration from say 0.1 to 0.2. Change in this concentration for the weak lambda value for the weak electrolyte, and the same value if you try to extrapolate to the strong electrolyte, this change in concentration is going to be relatively smaller. Delta lambda, the change in molar conductance for weaker electrolyte at most of the concentrations will be way greater in comparison to the change for the same concentration for the weak electrolyte. The reason is very simple. Two things. Weaker electrolyte are having the increasing value of the alpha, more number of ions are available. Because strong electrolytes were already about 100% dissociated, there is no scope of increasing alpha. They have got twofold effect, increasing alpha as well as decreasing ion-ion interactions. Cations, anions are going to be much more easily separated with the dilution. This is the dilution because concentration is increasing that direction. This is increasing dilution. So with increasing dilution, we are having the increased value of the lambda for both strong as well as weak. But this effect is much more greater in comparison to weaker electrolyte in comparison to strong electrolyte, because there one thing was already maximum. Alpha was already near maxima, like already about 100%. Weaker were much less than 100%. They are approaching 100%. So their change is supposed to be relatively way greater. Here we are having some more curves for more these kind of salts. Rather than having molar conductances, here equivalent conductances have been plotted, which will be having the correlation from the molar conductance as n factor. So if you multiply these conductances by the n factors, you'll be getting their molar conductances as well. So for example, KCl is having n factor of 1, sodium sulfate is having n factor of 2, copper sulfate is having n factor of 2 once again. So when we are talking about the molar conductances at infinite dilutions, then it is possible to surpass the molar conductance of strong electrolyte, but their strong electrolyte should not be having H+. Like if you are having here HCl, for example, if you see here the ammonia and acetic acid, they can surpass the limiting molar conductance of sodium acetate, and if we could plot it even further, this can possibly surpass the sodium sulfate. But we have to be very much clear about one thing, that acetic acid's limiting molar conductance can never surpass HCl, because H+ ions which are present in acetic acid will never be greater in number in comparison to HCl if we are talking about the same concentration. We'll be talking of that in a bit. Chloride and acetate, how they are compared, that also we can see. So we are saying this correlation is going to work very easily, and actually for the strong electrolyte, this is going to be a kind of relatively linear curve, but for a weaker electrolyte, this curve is going to be a little bit complicated. So for strong electrolyte, we can roughly we can see this is equation of a straight line. This is we call as Debye-Huckel equation. We have got many terms over here, and this is basically how the viscosity, the eta, and number of other terms are going to affect temperature, the dielectric constant, the charge, the attractive forces. Those things can be affecting. We can see in this case, this whole term for certain conditions can be remaining constant, that may not be changing. So we can be replacing this by some other constants. This thing we are writing as constant A, and over here this thing we are writing as constant B. And there was A naught term as well. Now even this, both the things A and B as well as lambda naught, because lambda naught for a given electrolyte is going to remain constant, we can write it as another constant, and that's going to be our simplified version of the Debye-Huckel equation. Lambda at a given molar concentration is going to be equal to lambda naught, that is limiting molar conductance. Molar conductance is equal to limiting molar conductance minus this is going to be some constant and square root of C. This is going to be our variation of the, like if you try converting this into a simple curve, this is going to look something like this. So this is going to be the value of the lambda naught m, that is limiting molar conductance, and this is going to be square root of C. So this is your lambda molar conductance, and its slope is going to be that constant. Minus slope is going to be the constant, which is A plus B A naught. So this is how we can see, we can basically calculate the value of the lambda naught by using this extrapolation thing. So say we have got some this concentration, this concentration, this concentration, and say we are talking about KCl, we know these values. Now we can extrapolate it and we can get the value of the lambda naught m for the strong electrolyte. But the problem is we cannot do so for the weaker electrolytes. In weaker electrolyte, what is going to happen? We are not able to extrapolate. You can see that curve, which is going to look something like that. Weak electrolyte is going to have this curve going to be kind of almost parallel to y-axis. So this is extrapolation over here is not possible. Extrapolation is possible in the strong electrolytes, where we are having these lines which are corresponding to some values, and you extrapolate it, you are going to have this point. This is going to be lambda naught m for stronger electrolyte. So for weaker electrolyte, when we cannot do extrapolation, we are using something different. We are using Kohlrausch law over there. What Kohlrausch law is, here we go. This is named after Frederick Wilhelm George Kohlrausch. He was a German physicist, and he suggested that the limiting molar conductivities, that is, the conductivities where concentration of electrolyte tends to be zero, that is infinite dilution. Sometimes we are using that word, that molar conductivities at infinite dilution. This for a given electrolyte is going to be basically the limiting molar conductivity of electrolyte, which we mean to say the conductivity is infinite dilution, are going to be related. How they are related? And there are two things. Number one, this is independent of its counter ion. So say if you are having sodium combined with chloride or combined with bromide, doesn't matter whether it's chloride or bromide. Sodium ion will give you the same contribution if it is at the infinite dilution. That is the meaning of independent migration of ion. So the conductivity, the limiting molar conductivity or the conductivity at infinite dilution for a given ion is not at all dependent on the counter ion. Does not matter what counter ion you take. It's not only about cation, it's true about the anion as well. So if you have some chloride ions, it does not matter what cation, sodium ion, potassium ion you are taking. Does not matter what you take. Any ion you take, the value for the chloride's molar conductance at infinite dilution is going to remain exactly the same. Also, this is equal to the summation. If you have taken some salts, sodium chloride you have taken, this is equal to the summation of the limiting molar conductances of all constituent ions. So sodium chloride will be, we'll be saying, this we can rewrite as sodium limiting molar conductance of the sodium chloride will be equal to the limiting molar conductance of the sodium ions multiplied plus limiting molar conductance of chloride ion. Say if it was MgCl2, for that limiting molar conductance would be defined as limiting molar conductance of the magnesium ion plus 2 times limiting molar conductance of the chloride ion. That's how this Kohlrausch law means. And it also means if you have got, say, in some case you had got lambda naught, say NaNO3, this would be equal to lambda naught Na plus and lambda naught of NO3. This also implies that this lambda naught Na plus, which is coming from NaNO3, and this lambda naught Na plus, which is coming from NaCl, they will be numerically same. They cannot have two different values because they are not dependent on their counter ions. This thing, they are not dependent of their counter ions. They will be having fixed values, and the summation of the value of the given compound is going to be equal to the summation of the constant of all its ions. So this indirectly also tells us that at lower dilutions, when the concentrations are going to be much low, then molar conductivities are in the proportions of their degrees of dissociation. Because if you are having more number of ions, more contribution for their molar conductance is going to be. So we can say now at 100% dissociation, when the concentration is going to be nearly zero, or when the dilution is going to be kind of infinite, then we can assume there is going to be 100% dissociation. And if the 100% dissociation is there, then we'll say the value of the molar conductivity will be reaching to its limit. That is what we are calling as limiting molar conductivity. Beyond that, we cannot increase the conductivity of any given compound. That was the meaning of limiting molar conductivity. We can be also calling as the limiting molar conductance or conductance at infinite dilution. Now coming back to our main question, we had got the correlation of K versus lambda m for the weak electrolyte. So this is going to be K is equal to Cl5 square divided by 1 minus alpha. This expression we have seen earlier. Another expression we have got this coming from the Kohl-Roche law, that alpha is equal to lambda m, that is limiting molar conductance at the given concentration, divided by lambda naught, which is at the infinite dilution. If you put these two expressions, basically substitute the value of alpha over here and over here, you are going to have this expression k is equal to c lambda m by lambda naught m squared divided by 1 minus lambda m by lambda naught. Simplifying further, this is going to give us this expression. So basically we are doing crisscross, and now we are going to write Ka terms on one side, and like this K is multiplied over here. This is Ka minus Ka times lambda m by lambda m naught, and this is C lambda m by lambda naught m squared. Now what we are going to do, we will be dividing this expression for the simplification by Ka times lambda m. We'll divide this expression. So this Ka term gets cancelled, and this is becoming 1 by lambda m, the leftmost thing. The second term, K lambda m by lambda naught m, if we are dividing by K lambda m, this is reduced to 1 by lambda naught m. And onto the right, this divided by K is going to give us C by K, and this is going to be lambda m. One square term gets cancelled, lambda m divided by lambda naught square. Because we want to plot a curve between 1 by m versus C lambda, we'll be transposing this terms onto the right hand side. That is going to give us the value of the intercept, that is C. We can be comparing this with y equal to mx plus c. This is going to be our term y. C lambda m was supposed to be our term x. So this thing is going to be our m, and this thing is going to be our c. That's what we are going to compare. Y is 1 by lambda, x is c lambda, that was given to us in the question, and slope is going to be 1 by k lambda naught m squared. That was s as per question. We are writing this as s, and the intercept was going to be 1 by lambda naught, which in the question it was told as p. Now what they asked, we had to find p divided by s. So we'll do p by s. This is going to be 1 by lambda naught divided by 1 by k lambda naught squared. That is turning out to be Ka times lambda naught. That was option number A in the question given. That was all in this question. And before we wind up, one more thing. In different places, you'll find some curves like that. If that strong electrolyte is there, it is fine. But the problem is sometimes they're writing this strong electrolyte as HCl, and they write this as weak electrolyte as acetic acid. As long as it is not HCl, if it is KCl or sodium acetate, as we have seen in the data set earlier, it is fine. But as you keep this acetic acid and HCl, this is going to be all very, very weird. This is not at all correct, and there is a problem. The problem is acetic acid cannot surpass the conductivity of HCl. We have a reason for that. Whatever be the dilution, the number of ions present in acetic acid solution for the same concentration for HCl, we cannot have more number of ions. Let us assume for a moment when we are having infinite dilution, the number of ions, say 1 mole H plus ion, 1 mole chloride ions are being produced by HCl, and the same thing 1 mole H plus ion and 1 mole acetate ions are being produced by acetic acid as well. We are having equally same number of ions, 2 moles of ions are present. Still, we cannot have the molar conductance of acetate ion greater in comparison to HCl ion, because acetate ion we understand is stronger base in comparison to chloride ion. Acetate ion will be more solvated. If it is more solvated, it will not be very easily moving. And if this is not very easily moving, this is going to be a curve which is never going to surpass the curve of HCl. That we have to be very much clear about. Although this kind of crossover is possible, but this happens at very, very, very low concentrations. We are having one data which can be giving you a better idea. This data is from Physical Chemistry, Electrochemistry, Dr. Rajiv Jain from JEE University. This is the curve. The first topmost curve is for HCl. This is for NaOH. And here we are having the bottommost curve is for CH3COOH. This curve was for AgNO3, and this curve was for KCl. So we have used here concentration 0.002, and this was some concentration somewhere about 0.0001. All these concentrations up to 4 decimal places, we have seen this curve. This value was about 0.0001, something like that. 4th decimal place, this value which was belonging to this. So 10 raised to power minus 4 concentrations when we have used this is how this actual data look like. If you go probably beyond this value, this shape of curve is telling you this can possibly intersect these two curves, KCl and AgNO3. It is highly unlikely, we have never seen in any of the data where the conductance of the acetic acid can be surpassing the conductance of HCl. That's all for now, and this was the longest of all the videos we have done as of now for a single question. Thank you, bye bye, see you again very soon. And if you find this discussion of even little use, please consider liking and subscribing, and stay tuned. Thank you, bye bye.